In this video, let us see some more examples to find out the natural frequency. Here in this case, this mass is connected with these two springs as shown in the figure. Now we want to find out the natural frequency of this mass. We know that the natural frequency omega n is equal to square root of g by delta static. Okay, delta static here in this case is delta static is equal to 2 times the deflection in spring 1 plus the deflection in spring 2. It is because, for example, this spring 2 is gone up by an amount x, so the total amount of rope that will be coming towards this side will be 2x, right? Similarly, this point came down, let us say, by x, so the total rope that is lacking due to the movement of downward movement of this x is 2x. So actually the deflections here will be multiplied by this factor 2. Now let us see what are the deflections in each spring. Let us consider this first spring. Let us see this first. This one is the pulley, and here mg is acting, mg. So we can say that mg is the total tension in the string. This entirely is the single string, right? So here also mg is acting like this in the string, and here we have the spring. So the total force in the spring must be mg plus mg, 2mg. Like that, if you draw the free body diagram for this one, spring 2, we have the ropes like this, and the tension is same everywhere in the string. Here is mg, and here also we have mg, and the spring force will be acting in the downward direction, and that must be equal to 2mg. So total upward force must be equal to the total downward force. So the spring force must be equal to 2mg. Here also we have the spring force in the spring 1 is 2mg. So our total static deflection is nothing but 2 times the deflection in spring 1 is nothing but the force in spring 1 by k1. The force in spring 1 is nothing but 2mg by k1 plus here also 2mg by k2. So we are getting 4mg into 1 by k1 plus 1 by k2. Okay. Or omega n, the natural frequency, is equal to square root of k by m, right? In other words, we can also write it as square root of g by delta static. if we write that, our final omega n will become 1 by 4 into 1 by k1 plus 1 by k2 into m. This is the natural frequency of this spring mass system. Okay, this will be in radians per second. Radians per second. If we want to find out the frequency in terms of frequency, or hertz in terms of hertz per second, this can be written as like this: 1 by 2 pi into square root of 1 by 4 into 1 by k1 plus 1 by k2 into m. This is hertz or cycles per second. Okay, it is because omega equal to 2 pi into f. Okay, if we want the frequency f, that should be 1 by 2 pi into omega. This formula we have used here in this case. Okay, so this is the final frequency of vibration or natural frequency of the system in radian per second. Next question is here is the 2 kg mass connected to springs like this, 10 newtons per mm. Here also 10 newton per mm. Okay, 10 newton per mm, and here it is 20 newton per mm. So for this configuration of the springs, what is the natural frequency of this mass? And we know that these two are in parallel case, so the equivalent stiffness of these two must be 20 newton per mm. So this 20 newton per mm and this 20 newton per mm are in series. Okay, here is our 20 and here is our 20. So the equivalent will be, equivalent stiffness in case of series is nothing but k1 k2 by k1 plus k2. Here both are same, so it is k square by 2k, which is k by 2, which is 20 by 2, which is 10 newton per mm. Okay, now the equivalent stiffness of all these three springs is 10 newton per mm, and this 10 newton per mm and this 10 newton per mm are in parallel. So the equivalent stiffness of the spring K equivalent will become 10 plus 10 here. That is because these two are in parallel. So it is 20 newton per mm. Okay, this is the K and the mass is 2 kg. So what is the natural frequency? Natural frequency omega is equal to square root of k by m. Here k is nothing but square root of, k must be in newton per meter. Here in the, to use this formula, k must be converted to stiffness of the spring must be converted to newton per meter. So this will become 20 into 10 cube by 2. This will give 100 radian per second. If we want to find this one in terms of the frequency in terms of hertz, f is equal to 1 by 2 pi into 100 or 100 by 2 pi hertz or cycle per second, cycles per second. Here is the next problem we have. This mass m of 3 kg is connected to these two springs like this. Now we want to find out the natural frequency of this system. Now these two springs are connected to the parallel because if the mass is displaced by an amount x, okay, the extension in the spring 1 is equal to the contraction in the spring 2. Okay, if the displacement is preserved, we can say that these two springs are connected in parallel. Okay, so if these two are connected in parallel, the K equivalent is K1 plus K2. K1 plus K2. This is not actually series. This configuration is actually making the K equivalent stronger, not the weaker. Don't confuse. This is not the series case. It is parallel case. So K1 is 10 plus 20, which is 30 newtons per mm. This also can be written as 30 into 10 cube newton per meter. Okay, now omega n is equal to square root of K by m, which is equal to square root of 30 into 10 cube by m is 3 kg, which is 100 radian per second. This also can be written as, in terms of frequency, f is equal to 100 by 2 pi cycles per second or hertz. That means this value, its value is nearly equal to 16 something. So we can say that if you vibrate this, if you just disturb this mass, okay, it will vibrate with a frequency of 16 cycles per second. It will vibrate 16 times per second. Okay, so this is the natural frequency in terms of the hertz, and 100 is the natural frequency in terms of radians per second. Here we have another natural frequency problem. This is a U-shaped tube, and this liquid is filled here in this. All this is the liquid inside this tube. Okay, this is the mean line. So if you disturb this water, it will start vibrating, right? Then what is the frequency of vibration of that water column? That one we have to find out, where L is the total length of the water column, A is the area of cross section of this tube, and density rho is the density of the liquid. So here is the mean location. After disturbing this, let us say we have disturbed this water by an amount x. Okay, if this is an amount x, this will go up by an amount x, right? This will go up by the same amount x. Okay, to solve this problem we can use the energy method. Energy method is nothing but the derivative of potential energy and kinetic energy is 0. Kinetic energy plus potential energy is 0. Here Ke, the potential Ke kinetic energy is nothing but half m into x dot square, half m v square, actually half m into x dot, this is the velocity square, this is nothing but half m is the volume into density, mass is the volume into density, volume is nothing but A into L, this is the total mass of the volume, okay, this is the mass, Al into rho, Al is the volume into density, that will give us the mass into x dot square, this is the Ke term, and we have the potential energy P. See, to disturb like this, we have to apply some energy, right? If we plot the force with which we have to apply with distance, initially there is no need to apply any force, but that will increase gradually, linearly like this, right? Okay, and the value here is nothing but whatever the force we have to apply here, that must be equal to the total weight of this water column, from here to here, that is the total length of the water column is 2x into area, this is volume, into density rho into g, this entire thing is the mass into g, is the total force we have to apply finally after traveling a distance of x, this one. Area under this plot, f into distance plot, will give us the energy, this is what the energy we have spent to bring this disturbance in the water. So the area here is nothing but half this one into this one is nothing but base is x into height is 2x into A into rho g, this is nothing but x square A rho g, x square A rho g, x square A rho g. So this will become the potential energy. So sum of these two, derivation of sum of these two must be equal to 0. Let us do that. It is half a l rho, here it is 2x dot into x double dot. This is the derivation of this term, plus the derivation of this term is nothing but a rho g is constant. This will become 2x into x dot. This is equal to 0. So this 2 will be cancelled, x dot will be cancelled. Okay, this a rho will be cancelled, a rho will be cancelled. We are left with l x double dot plus 2g into x is equal to 0. We can compare this equation with mx double dot plus kx is equal to 0. Okay, if we compare with this equation, m is equal to l, k is equal to 2g. So our natural frequency omega n is nothing but square root of k by m, which is the square root of 2g by l, 2g by l radians per second. So this is the natural frequency of this water column. Next question is the equation of free vibration of a system is d square x by dt square plus 64 pi square into x equal to 0. Its natural frequency is dash hertz. He is asking the answer in terms of hertz. So let us consider, if we consider any spring mass system like this is m, and if we disturb by an amount x, it will have some acceleration. Okay, so our force x double dot will be acting in the downward direction, and mx double dot, which is mass into acceleration, will be acting in the upward direction. Okay, and this spring also will try to pull this mass upward by an amount k into x. So these two are the forces acting in the upward direction. For the equilibrium, the sum of these two forces must be equal to 0. So the equation will become mx double dot plus k into x is equal to 0. And we know that the natural frequency of vibration of this mass is omega n is square root of k by m. If we compare this equation with this one, this is nothing but x double dot plus 64 pi square into x is equal to 0. Okay, the mass m is equal to 1 here, there is nothing, right? And k is 64 into pi square. So the natural frequency omega n will become square root of 64 pi square, which is nothing but 8 pi radians per second. But if we want in terms of hertz, the frequency f is equal to 1 by 2 pi into 8 pi, which is 4 hertz. The answer is 4. Let us see the next question. A spring of stiffness K is cut into 4 equal parts and are placed in parallel. What will be the stiffness of the new spring? And this is the, let us say, one long spring is there. Okay, and the stiffness of this entire spring is K, he is saying. And if we don't know, let us make it 4 parts. Let us say A is the stiffness of each and every spring, and all these are, we can say that all these stiffnesses are connected in series, right? So the equivalent stiffness 1 by K equivalent must be equal to 1 by A plus 1 by A plus 1 by A plus 1 by A, which is nothing but 4 by A, or A is nothing but 4K. That means the stiffness of each smaller spring, the small spring, is 4K. Okay, so we can say that the stiffness of the spring is increased by 4 times by reducing the length by 4 times. So this each small spring is connected in parallel, he is saying. So each small spring is connected in parallel. 4 springs are there. And each one is having 4K stiffness, 4K, 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 like that. So the resultant stiffness of this combined new spring will become, since they are connected in parallel, 4 times 4K, which is 16K. K equivalent is 16K. Here we have one more question. A mass of 3 kg is fixed at the center of the spring of stiffness 15 kilonewton per meter. Find the natural frequency of the system. Let us say that, let us assume a spring like this, and mass is attached here, and the mass is 3 kg. Okay, now we can say that these two parts will be in parallel. These two parts will be in parallel. Okay, this 15 kilonewton per meter, initially whatever the spring is there, it is nothing but we are basically cutting that spring here at this location. We can assume like that. So the stiffness of the each part will become 30. If we reduce the length of the spring by 2 times, its stiffness will increase by 2 times. So this will become 30 kilonewtons per meter, and here also it will become 30 kilonewtons per meter. 30 kilonewtons per meter. So, and again these two springs are in parallel again. So the total stiffness K equivalent will become 60 kilonewton per meter. So the omega n, or natural frequency, is nothing but square root of 60,000 by 3 kg, which is square root of 20,000. Which is 141.4 radians per second. It is because root 2 into 100, right? If we want in terms of hertz or cycles per second, the frequency F is 141.4 by 2 pi hertz or cycles per second.